Good afternoon, everyone. Welcome to my dissertation defense. I am Tanmoy Choudhury, and my dissertation committee members are Dr. Jhao, Dr. Sashan, Dr. Purohit, and Dr. Hong. My dissertation topic is cross-domain reasoning based on graph deep learning. There are mainly three parts of this presentation. One is research overview, and there is research areas and conclusions. So, research overview. I will start with case study, and I will use this case study to link all of my research areas. And mainly, I have two research areas here, the branch of my dissertation. You can think about like multitask learning and task relation reasoning and how they are all connected with each other. So now start with the case study. First of all, what is a spatio-temporal event? Spatio-temporal events are phenomena in certain locations and time. So take this one as an example. This is a civil unrest data from Brazil, 2013. You see these locations, there are different protest events are happening, right? Then take another example that is influenza like in illness. And here is the outbreak in southern region during 2014. So I'm going to use this one, influenza like illness, throughout my research overview. And I will explain all of my research works according to this one. Okay, so let's start. First of all, we want to do the event forecasting. So if we want to do event forecasting, we can do one for all model. We just design a model, take the data from different states of USA and predict the event that, okay, what is the influential activities, right? And the pros here is that we would have sufficient data to train model because we are taking a lot of data, right? But here is the cons. It ignores the individual states' exclusive characteristics like size, population. So if you see here, Virginia, California, Texas, they have different areas and different populations, right? So then we can think about that, okay, how about we use one-to-one model? And that times, of course, it have the pros, like it will consider individual locations' exclusive characteristics. But it comes with the cons, that is, it ignored the relatedness among different locations. Like some locations maybe shared similar expressions, same languages, shared keywords, relevant events, similar topics, right? And also, there are insufficient data for small locations. If you look at the tweeters, that time you will see there are very few cities, they have tweets a lot. But most of the cities tweets very small amount, right? So we see both pros and cons of this one for all model and one-to-one model. What can be the solution? So considering the pros and ignoring the cons, the solution can be multitask learning. Now, if we think about the design of a multitask learning, you have the task, you take the data, you design the model, then you predict the event. Here, all tasks means separate states. Now think about there are parameter sharing. It can be soft or hard. So if you see, there are linkage between here. And this linkage, this is the constant layer. So these constant layer actually are designed based on the task relation. There comes our first research question, that how to implement the task relation, because this task relation can be different, right? So take this one as an example. This is a spatial relation constant. So what you see in the same example, ILI activity, if you look at here, you would see that these are mostly green and southern region most are red. So that means there are some similarities, right? So this is called geographic rule. And this geographic rule, you can actually find out in different domains like climate zone and also in like USA states, similarity index. So climate zone, you see, there are different climate zones and they are sharing the same characteristics in the same zone. And also, even if you take the demographics, culture, politics, infrastructure, geography all together, that similarity index also follow the same rule. So there is a spatial relation which we need to implement in this multitask learning. So there comes our first work. That is a spatial relationship we focused on, where we capture this spatial heterogeneity that becomes a non-convex and strongly coupled problem. We implement that one for event subtype prediction. And that is one of our work for multitask learning. Now think about, and also the model we proposed here, that is detective. Now think about temporal relation. So take this data from 2019 with 45 ILI activity. Then next week, if you see here, the Louisiana was affected. Then Louisiana effect changes, and also the other things are changing. So other states relation is changing. And then the whole southern region was affected. So here is a temporal relationship and also temporal delay, right? So this temporal relationship, each week you can think about like a time stamp. And each time stamp, the attribute of those states, like the task and the relation among them, can be changed. So considering this one, we think about this temporal relationship, we design a dynamic graph and also implemented hierarchical attention. For real life implementation, we implement this work for sequence generation. That comes our other works, that is multitask learning. So what we see, and here we propose the model that is dynamic attributed graph to sequence. Now from this, we see that we have a issue how to implement this task relationship in the constant layer. Based on that issue, we work on this spatial relationship and temporal relationship work, which actually make this multitask learning of this dissertation, right? Now, and here is the two models, detective and dynamic attributed graph to sequence. Now we can say we take those pros and we get this multitask learning. There was a challenge designing the constant layer based on task relation, and we overcome that challenges, right? But still, it is still a cons. Why? Because it requires a predefined task relationship. So there comes the second research questions. What would happen if we do not have a predefined task relationship? Because the previous two works totally based on task relationship we already had predefined. Now, what would happen if we don't have that relationship? So there, I'm going to give you another example. Take this one example. Week 3, January 18, 2020. What you see that our influenza level activity is already worst in USA. And there comes our nightmare, COVID. The first COVID case was reported on January 22nd, January 20, 2020, right here. Now, look backward. Look at this graph once more. You see this special rule, what I have already discussed, that similar adjacent states are sharing similar type of patterns. But still, there are something, what it is. If you look at here, Washington state already has that COVID case, but why Virginia and Washington are showing the same influenza level activities? They are not adjacent, right? So even during the COVID period, if you look at the situation of the COVID situation of Washington and Virginia, they followed the same pattern. And also, if you look at the graph, until 2023, still now the COVID actually follows the same pattern in Washington and Virginia. So there comes the question that why Washington and Virginia are similar, right? But we do not know, because special rules, what we showed here, it looks like that Virginia, Maryland, DMV areas is okay, but why it is? So there, that means maybe there can be connections. How they are connected? As just from a human perspective, Washington and Virginia, you can think about like a road trip, airline trip, and also the shipping, right? But if these are the path, this is just I am showing this just a traveling path, but it can be different way. It can be connected. Virginia and Washington can be connected in different nodes, different ways. So that is path relation, and that path relation can be different for different perspective. So think about this one like an electrical circuit. Electrical circuit has different components. They are connected with each others, and this signal flows through this. And also, if you see, this is the first one, then this comes the first one. So this connection first comes, then comes. Here is the hierarchy, which path after which path, right? So based on all of these consideration, and we think about and we work on this research, that is, we take those node heterogeneity, like think about all of these node as a states, right? Node heterogeneity, then the path hierarchy, like they have some path hierarchy. Based on that one, we design a model and we implement that model for static timing analysis. And that is one of our work for task relation reasoning. And the model we mentioned, design here, that is called RAPTA. Then another way, think that what is the georesolution levels of connections between Washington and Virginia can be. they are states of USA, but of course they have some county, like Skagit, Snohomish, or we have Fairfax, Arlington, Loudoun, Prince William. So these geo-resolution level of connections can we utilize to find out the relationship between Washington and Virginia. If I want to say in a technical term, how can we do the analogical reasoning? How can we say that Washington and Virginia are analogous states, right? So there comes some questions like what is the relation in each state? How to map node from one state to another state? And when two states are analogical? Think about only Washington state. It is like a graph. You take all the relationship from Washington state. So Skagit is a county of Washington state. Like Snohomish is a county of Washington state. Again, Skagit and Snohomish are neighbor. Skagit and Snohomish health conditions are same. So this type of relation you take together, make a graph for Washington state only, right? Same way, take this Virginia example. Maybe you have more information for Virginia, so your graph can be more complex than Washington. So think about this Fairfax and Arlington. As I explained, they are county of Virginia, neighbors, and their health condition are same. Then there can be another relation, like Fairfax population is greater than the Arlington population. Again, Arlington can be a tourist. Arlington is a tourist spot, right? More complex, if you go, that they are county of the same state, and also they are neighbor. So then that's why their health behavior quite similar, and that's why their health condition is same. So this type of relationship, you take this. So you have totally different Washington state and Virginia state. Now, can we make this analogous? Then if we want to say Washington and Virginia are matched with each other, that times we need to maintain something. What is that? First of all, if they need to be mapped, that means their children should also be mapped. Okay, so their children, like county. So county level, geo-resolution level information that I said, they are matching. Are they matched, or how they are connected? Then there comes the one-to-one relationship, and also there comes other things like systematicity. What is your system to prefer which node you want to match with which node? So using these type of things, you can do the analogical reasoning. I will come back to this topic again when I will discuss my research areas. But for right now, we just consider this. Another issue we have, that is analogical reasoning. How can we do? So we have issue like we do not have the task relationship. Then we want to find out the task relationship. And here we want to apply the analogical reasoning. Based on that one, so think about, we did the research on analogical reasoning, where we take the graph heterogeneity, node hierarchy. So previously in path reasoning, we take the node heterogeneity. And now here we take the graph heterogeneity. That times we take path hierarchy. Now we are taking the node hierarchy. We implement that one for a real life implementation, knowledge transfer. That is our another word for task relationship reasoning. So finally, and there is a model we propose, that is DeepGAR. So what we see, that this would say, this is a con, that what would happen if we do not have, firstly, we of course focused on how to design this layer. Secondly, we focused on that what would happen if we even do not have the relationship, can we extract that relationship? So based on that one, we propose two models, RAPTA and DeepGAR. So in a nutshell, my dissertation topic is cross-domain reasoning. And it has two things. One is multitask learning, another is task relation reasoning. And for multitask learning and task relation reasoning, I have 4 works. One focused on the spatial relationship, temporal relationship. Then for task relation reasoning, path reasoning, and analogical reasoning. These complement each other. So during my proposal, I already presented these 2 works, path reasoning, RAPTA, and also this dynamic attributed graph to sequence. Due to time constraint, after that, I developed these 2 models from this one, from these 2. And for today's, due to time constraint, I will only present these 2 things, spatial relationship and also the analogical reasoning. And of course, I just want to mention those 4 names again: detective, dynamic attributed graph to sequence, RAPTA, DeepGAR. These are the 4 models in my dissertation. So that's all for my research overview. Just have a look. I would say maybe 5 more seconds to this link. Okay, so let's start with research areas. As I mentioned, my research areas, of course, this is cross-domain reasoning, and there are multitask learning, task relation reasoning, and for there's two model, detective dynamic attributed graph to sequence, RAPTA and DeepGAR. I will start with detective. So detective, it means like deep multitask learning for a spatio-temporal incomplete qualitative event forecasting. Okay, so we start with the event prediction. Event prediction is the capability to estimate the possibility that some events may occur in a specific time. Stick with the same example of ILI activities. So here it can be disease outbreak, right? How we need to predict the disease outbreak. So this disease, why we need that? Because it will help us to allocate appropriate level of resources, like for vaccination, for isolation. Now, this flow activity, you can consider this like a class problem. Okay, this can be minimal, low, moderate, high. Or you can consider it like a scale problem. That means you need to maintain that, okay, of course, there is among different subtypes, there is a relation, and you need to maintain the order. So there are different ways you can think about this problem. Okay, conventional methods like multi-class classification methods, logistic regression, moving average, linear regression, SVM, etc. So, but most previous research in this area actually focused on the temporal event. And existing work providing that a spatio-temporal resolution of predicting event mainly focuses on the occurrence only. It's like a binary decision. Okay, this high level will happen or not, and are not able to handle the specific subtype of featured events. So some works used multi-instance learning for event subtype forecasting. But here is the thing. When you use the multi-instance learning, that times it studies the problem in which level are assigned to bag of containing multiple instances. So maybe you can say that, okay, level medium will happen for Texas, Louisiana, or even Washington, California. But what is the relation? Why? So that thing is totally ambiguous. In contrast, if the thing we are following, that is multitask learning, it focuses on the output space in which an input sample is associated with multiple levels. So the Texas will be assigned to multiple levels, then from there you choose. So that is the thing of multitask learning, right? And most importantly, among all of those work, there was no generic framework is proposed which can handle different types of subtype problem altogether. So if you want to consider that one as a multi-class problem, then you need to design a multi-class problem. But that model, you cannot use that for multi-scale. So there we developed a model, one model solution for all different types of problems. These two are just an example, but you can use that one for others also. Now, among those related work, there are two popular categories of event prediction. One is scale prediction, another is class prediction, right? So for scale prediction, take one example like proportional odd model. It can be seen as an extension of the logistic regression model to the ordinal settings. And class prediction, you can think about softmax regression, right? It is a generalization of logistic regression that we can use for multi-class classification. Of course, under the assumption that the classes are mutually exclusive, but here the classes are not mutually exclusive. Okay, so here it is. Think about like this one, POM and softmax. Of course, we know that in case of POM, there is only one shared weight. But here, in case of softmax, you have different weights for different classes because they are mutually exclusive. Then for ordinal response, they just use the threshold and then you determine, okay, which level it is. And the same procedure follows for the softmax also, multi-class prediction. So what you see here, it's kind of like a game of weight and bias, or you can say threshold. So let's play the game. Now, there comes the challenge. So why we cannot directly use this POM or softmax for a special event scale forecasting? Because I have already showed that one, right? You can ask me this question, why we cannot just use that one? There comes the issues and challenges. First of all, heterogeneity of event subtype. So these event subtypes has heterogeneity. Then also incomplete level in special event subtypes. And there another reason is that spatial correlation of event subtype pattern. I'm going to describe these three challenges right now. So first of all, spatial heterogeneity. Different locations have different characteristics, such as population, weather, administrative structures, right? So the population in California and Nebraska are not same. So if you see that, okay, same number of keyword clue can lead to different activity scale, whether in California and Nebraska, they would be different. Then also topic participation varies based on region. I would like to take this one example. It's a very interesting thing, like beer and charge tweets. If you consider these two things, you would see that southern regions tweets much more related to charged, right? However, here in this region, people are tweeting more related with beer. So you see the spatial heterogeneity matters. How people are participating there, and even if they are participating, what is their count of those things actually different, right? Then there comes other issues, incomplete labels within tasks. What is that? What does it mean? So for any given location, it can happen that some event subtypes are not present within the period of time chosen as training data. Take this. So think about these things like Texas, Louisiana, Alabama, Georgia. Okay. So if you see here, maybe Texas never faced the influence activity level 3, and Louisiana never faced 1 or 2, and also Georgia never faced 1 in historical data, what the training data we are using to train the model. But Texas never faced level 3. It doesn't mean that it will not, in future, it will never face that one, right? So but now the problem is, when you use the data-driven model, and if you didn't see the data, the model cannot predict. So here is an incomplete level. So that times when we are training data, there is an issue of incomplete level things. So this is one of the issue. So this is a crucial challenge, and as not handling it can lead to impossible of predicting the subtype that are missing. So then the things I want to again refer from my research overview portion, that is spatial correlation, right? Spatial locations are not independent of one another, but instead are correlated by following spatial topology. So if a state has a high fluid activity level, it is most likely its adjacent states also has high fluid activity, like these figures, right? So this is called the first law of geography. Everything is related to everything else, but near things are more related than distant things. So by sharing data between the adjacent tasks, it also helps to handle the incomplete level challenges, the one I discussed just in my previous slides, right? So as adjacent tasks will try to complement each other's information. I just want to again mention that task here means each states here, okay? So I have discussed the related works, and here is the problem, and here is the challenges, what we are going to address. So what it looks like. This is our model framework, just like think about the skeleton. So you have the input sample, then for each task, you are trying to forecast the event, okay? So take input data like task, you have task as, then time and features, okay? So generally, deep learning framework, just simple way think, it is just a main objective function of this one. Here, this function f, look at here. This one, we design in such a way that based on your requirement, like if you want to do multi-class, or if you want to do multi-scale problem or other problems, that times you can actually plug in that function here, and still our model will able to achieve that task. So that's why we designed goal-specific functions. Well, these two are just an example. Like if you have multi-class problem, you use this function. If you have so how you can do that one? So you start with here, you have the data, then you use this multi-class prediction. If you remember from the research overview, there are different types of weights for different types of different subtypes, because it considered all the subtypes are mutually exclusive. And also their bias, how you choose. So this is your multi-class prediction. Then it can be multi-scale problem. In case if you have multi-scale problem, you instead of using this function, you plug in this function here, right? So you start with the input data. Then use the scale prediction. That means you see here it has a lot of weights, but for each task you only have one. For different types of subtypes, you do not need different types of weights because this is a scale problem. But here you have different types of bias or threshold which are going to maintain that ordinal regression and also want to predict that scale of each state. Okay, so that's how we can do the prediction. So you see, deep learning framework, we make it a generic, but still we use two constraints so that it can be more generic. And if we want to, can maintain this type of constraint in this generic framework, and it will help to achieve the goal. So from here we started. Now we created that generic framework, the same equation here, and we use two constraints, one for weight, another for bias. Now start with that generic framework again. Still you have the question, right? That, okay, how about that spatial heterogeneity I was talking about, or the geographic rules I was talking about? So if you look at here, so the ratio of the probability of being belong to two types of two tasks, like IJ, close in geospatial distance should also be similar. So this is kind of, this is like the geographic rule. And based on that assumption, we can say that, okay, probability of, like, let's say here, this Texas has the probability being in low level 1 and also being in level 2. This ratio is also same for Louisiana, like this one, C1 and C2. So this one, if we can maintain this ratio, this will help us to maintain that special geographic rules here. So based on that one, this simple generic framework, we started to introduce two more regularization terms for weight and bias, and still we have that constraints only to make it a more generic for different types of functions. So take the example of multi-class problem. Okay, just for on this side. So for multi-class problem, I started with this generic framework, and after that, the main objective function, as I said, I am going to plug this function with the multi-class function. Then this LB WB file looks like this one, but as we are considering W and B all together, just for simplicity, I just mentioned this one as like a big theta. So it will make the equation more simple. So now for the regularization, here we do not need that regulation right now. What we did, that we considered this weight and bias all together instead of just only considering this weight regulation, because we know that these subtypes are mutually exclusive. So we need to consider this weight bias this way. And that's how we designed that regulation term beta B2, beta R2. Okay. So overall objective function looks like this. Based on that one, if we want to right now, if we want to optimize this function, it becomes as I said, it becomes non-convex and strongly coupled. So that's why we followed divide and conquer. We used an augmented Lagrangian form of the objects. Then we used the algorithm of ADMM, design an ADMM algorithm to solve this equation, to optimize this equation. That's how we did. We can implement our generic framework detective for multi-class problem. Then there comes the other one, that is detective S, where you can implement that one for multi-scale problem. So start with the same way with the generic framework. Then main objective function changed based on this function. And after that, we know that they share the same weight for all different types of subtypes. So we have the regularization term for weight, and also these bias, they are different for different subtypes. That's why we implement this another regularization term here, this one. So based on that, the main overall objective function looks like this, where we maintain two constraints. One is WSC1. Sorry. Okay. So here is WSC1 is equal to WSC2. What does it mean? It means that we have only one weight for all type of subtypes. This is one of the constraints, and another constraint we maintain, that is these biases or these threshold need to maintain the ordinal relationship. So based on this way, you can use this detective for multi-scale problem also. And here is the ADM augmented Lagrangian form to use ADMM to solve that. Now, as I said, okay, how about the experiment? So Take this experiment for multi-class problem. I did that experiment for this one, that is the event forecasting for civil unrest. And here we see that our model actually improved the baseline things 10 to 25%. And also, I did the experiment for China data. There we see that our model can outperform the baseline model by 5 to 10%. Okay. Here, take another, also one more thing I want to mention, even you can use it without deep learning layer. So without deep layer, without any kind of deep learning layer, even you can directly use that one, that is this model. Now, if we look at the original data, like what is the air pollutant subtype distribution in China, this is the ground truth. And this is what we find out based on our model detected. And this is generally what SBM can find out. Okay. Then for experiment multi-scale problem, again, our model outperforms the base model by 2 to 30%. And we also did this experiment for civil unrest data and also US flu data. And if you see here, US flu data also, we improved that base model score to 13%. And if you see the heat map, like different types of subtypes, odds, and here is the threshold difference in different types of regions based on our model, this follows the quite similar pattern. So look at here one more time. I picked to explain one thing from multitask learning. That is, I explained here, that is a special relationship, and it is one of the part from my cross-domain reasoning. Now, let's start with the second topic, that is task relation reasoning. And for that task relation reasoning, I'm going to explain this analogical reasoning. Okay. I just want to take 5 to 10 second break, please. Okay, let's start. So now there comes the model DeepGAR, deep graph learning for analogical reasoning. This is the second part of this, another branch of my dissertation, that is task relation reasoning. Why we are doing this task relation reasoning? Because we already developed MTL when we can implement that MTL when we have the relationship. But what would happen when we don't have the relationship? That's why we are doing task relation reasoning to extract the relationship so that we can again implement that one for MTL also. So here we start with the DeepGAR. Okay. Same example, taking that example, Washington and Virginia, how they are analogous. And I explained a little bit all of these things in research overviews. From there, the question you may ask that why analogical reasoning? Why you are doing analogical reasoning? What is the problem? Why you just don't go for literal similarity, abstraction, anomaly? There are a lot of ways, right? Take the example, like literal similarity. The K5 planetary system is like solar system. And then analogy, the atom is like solar system. Or abstraction, the atom is a central force system. Or coffee is like the solar system. It is called anomaly. Why we are taking this analogy to make the similarity? Because if you see analogical reasoning, less focused on the attribute, it's mainly focused on the relationship. So it can help us to make a lot of many relationship mapping. That's why we chose to use this analogy to find out the relationship between totally cross domain to distinct domains. How can we do that? Okay. So analogical reasoning, then the question comes, what is analogical reasoning? Analogical reasoning is the process of transferring or mapping information from a particular subject, you can take it as a source, to another particular subject, to target. So take this one as a source, maybe this one is Washington State, this one is Virginia. You take the concept from Washington State, implement in Virginia. Okay, this is the analogy. And for example, we may transfer the knowledge from Washington to Virginia, as I said. Now, structural mapping theory, how you can implement this analogical reasoning. We understand the main concept of analogical reasoning, but how can we do that? So there comes that structural mapping theory. So SMT was developed by the Deirdre Gentner, yes. And it actually distinguishes analogy from literal similarity. It recognizes that there can be differences between base and target. It's okay to have different domain, but make no difference to the strength of the analogy. example, the popular example, Rutherford atomic model, right? But we are going to use the same concept here for Washington and Virginia. So use the same concept, and I am going to go a little bit more about the relationship. So you see, this is called object. This is the attribute, because it only have one relation. This is called attribute, and this is called the relationship. But the relationship can be different way. It can be first order, a second order, fourth order. The problem is all the people doing the knowledge graph mapping or anything mostly focused on the first order. They do not do the second order or fourth order things. But if I can implement this SMT theory for deep learning, that times I can actually go logically for higher order. So you see here, so these are the things as SMT focused on. It can go for more higher order relationship. But you need to maintain four things, mainly for SMTs. That is one-to-one mapping, how you map one-to-one. Another thing is parallel connectivity. These are parallel. You see, this county versus county, county versus county at the same level, parallel connection. Tired identicality. So tired identicality is kind of like a tricky thing. So it is not necessary that this county matching with county. Fairfax, maybe instead of considering the whole Fairfax city, you can or whole Fairfax county, you can just consider Fairfax city. Still, you can map that one with Skagit County. So that is called tired identicality. So it is not strict you that, okay, you have to be same. No, no way. Then comes the systematicity. So how you should choose? So you can ask me that Washington looking like the second order relationship, but greater is also second order relationship. Like Fairfax population is greater. Why we cannot match this node with this node? Just focus on the relationship. Don't care. Don't think about the attribute. But still, we cannot do that because Virginia, this node actually belongs to higher order of relationship. So that is called systematic preference. When you have this type of two matching, that times what you choose? You choose the one which actually has more hierarchical things. So that is called systematicity. So we need to maintain these four things. Otherwise, we cannot implement this SMT for analogical reasoning in deep learning. So there's related work. Most prior deep learning works actually involves the explicit graph matching. They didn't do that analogical reasoning. So in structural mapping literature, but in SMT, you do not require explicit graph matching. It involves only relationship. And the first work which implement this SMT in deep learning was the AMN, neural analogical reasoning. And we are actually the second one implementing this analogical reasoning here by using deep learning. So the drawbacks of AMN is that it does not make the use of node level information. It just, yes. So, but also it employed element-wise comparison. That's why it takes time. And also it values the nature of analogical reasoning since they can only output isolated correspondences one by one, not all together. So that's why, how can we implement of SMT? So first of all, we considered these Washington and Virginia, they share commonalities, and SMT gives us a symbolic way to perform the analogical matching. What we did, that SMT allows us to represent this as a target graph, this as a base graph or base subject, okay? And in the form of directed acyclic graph, we maintaining the directed acyclic graph. Then we can formulate the analogical matching as identifying subgraph one by one, maybe taking two hop graph, start from top, and we start to matching that way. That's way we can implement the SMT. Think these two states. Now, if I just only take the county level information event, this 37 is county, and I have in Virginia 139 county, how complex it is. So this complex level, and if you consider all the relationship, it becomes a very complex graph. But yet, still, you can do the SMT if you consider about like a subgraph matching. So you take portion of the graph and you start in Washington state and you start one by one mapping, one by one, take one by one subgraph, one by one subgraph. When you match, lock it. Start to one matching with node to node. That's how you can do the subgraph matching here. So, but what are the challenges we see? That here is a difficulty in locating structural alignment between the base and target object. Why? This graph, take this one again, and you see there can be a lot of possibilities. It's the NP-hard problem. How you can choose the best one? Washington can be matched with different types of nodes, but how you choose the best one? So you see, it becomes an NP-hard problem. And also its difficulty in considering unique constraint throughout the correspondence. As I said, SMT satisfied 4 things like parallel connectivity, one-to-one matching, systematicity. These constraints we need to maintain. So there are 2 challenges here. And so now what we did, we considered this one as a problem formulation of an alignment matrix. So think about, these are all the nodes from Washington. These are all the nodes from Virginia. Now our goal is to match only one. Through the column or through the row, there will be only one matching. If we can maintain that one, then those from huge amount of matching, we can just choose only one. So that's how we considered to do this one. So here are these 2 challenges. As I mentioned, a structural alignment, challenge 1. For that one, I designed like a constructing an embedding space that directly captures the subgraph relationship. And also the challenge 2, that design a novel end-to-end inference objective to search relation alignment. So this one, for solving challenge 1, I designed this mapping. So if you see in the representation space, if you take 1 by 1 subgraph, so whoever has the higher order, it is actually presented in Euclidean space also in higher order. So A represent here, C here, the same way D like here. So we use geometric embedding so that we can maintain this relationship hierarchy also in the embedding space. That's how it becomes more easier for us to choose the node. Then also what we did, this is the, so then there comes those constraints like unified objective for locating the analogical matching. What we did, here is the objective function for parallel connectivity. This portion of our equation maintains that parallel connectivity constraint. Then one-to-one was maintained by this constraint. Then tiered identicality, we also maintain this tiered identicality like the relationship expression. And also the systematicity preference should be given to the mapping in the deepest. So as I discussed, there are 4 things we need to maintain to satisfy the SMT, and this is how we maintain this things. So these are the augmented Lagrangian form of that objective function, which we used for optimization. And for experiment, I did all of this. I did this experiment. And here I see, I considered analogical matching approaches and subgraph matching approaches, these 2 challenges. So we did this one for synthetic data and also real world data also. Then considering these from analogical matching approaches, as I mentioned, AMN was the first and our model is the second in this field. So compare this, our model with this one, we see that our one has very, actually beat AMN. So DeepGAR demonstrates competitive results and excels AMN in most cases. Similar way, neuromatch. And also there are other things that is kind of like using the subgraph matching technique, but not doing the analogical reasoning. So that neuromatch, when we compare, we see the neuromatch actually does not illustrate comparable result since it is not able to locate subgraphs that fit the analogical validity constraints, that 4 constraints. Okay. So key takeaways, we propose an end-to-end framework, learning framework, DeepGAR, produces analogical reasoning, analogical correspondence, then consistent with the constraint regulated by SMT. And here DeepGAR learns the relationship between subgraph with graph neural network and geometric embedding. Then DeepGAR locate analogical correspondence with a unified objective. Look at my dissertation all topic again. I explained one topic from multitask learning and another topic from DeepGAR. These 2 altogether make my dissertation cross-domain reasoning. Now come to the conclusion. This is, as I mentioned, this was for data-driven approaches and proposed presented in proposal, and there is the final defense I presented here. Now you can ask me that, okay, why I did cross-domain reasoning only based on graph? How about the other situation of reasoning, right? That's why I also did a very extensive literature review. Based on that one, I found that people use knowledge enhanced reasoning in explicit way, implicit way, that can be pre-trained, memory augmented, knowledge graph, knowledge rule, and there also it can be generative, discriminative, external memory, and this way. So from different type of branches, I finally found out. But this is a huge research area. I cannot cover in one dissertation topic. So I only focused on the knowledge graph and encyclopedic one to show the cross-domain reasoning here. So in future work, I have planned to extend my work in other branches. And also I submitted this paper in IGCAI. So finally, what is the broader impact of this research? For detective, we use this generic framework for event prediction. Then dynamic attributed graph, we showed the real life implementation for healthcare. For RAPTA, heterogeneous, and that is called the path reasoning thing, we use that one for static timing analysis. And actually, this is the very first work in the static timing analysis field that utilizes raw features without human intervention. Then there's another thing, last one, that is DeepGAR we used for knowledge transfer, where we actually implemented that structural mapping theory. So here, this is the ultimate task and status. These two tasks, this is the thing, cross-domain reasoning based on graph deep learning, and these two are presented in our preliminary proposal. These two work I presented today, and I also did the literature review. Among these, I published in TKDE this first work, then second work in GL-VLSI. This work I have already submitted that literature review. TKDE is ready to submit. I'm going to submit it by next week, hopefully. And also DeepGAR already published in ICDM 2022. So these are the 5 publications directly related with my dissertation. Before that dissertation, I had other 2 publications. Finally, I want to convey my special thanks to my committee members, Dr. Zhao, Dr. Avasta Session, Dr. Purohit, and Dr. Ray Hong, and also to my collaborators, especially Dr. Yuan Gao, Dr. Ashkan Bakil, and Chen Lin. They helped me a lot to do all of these researches and to make all of these connections. I'm grateful to them. So any question or comments, you can reach me by email. Thank you.